So it's a great pleasure to welcome David Charbonneau, today's Colloquium speaker. He actually did his undergraduate studies at the University of Toronto, where so much exoplanet research is done today. But then he decided to move to Harvard to earn his PhD in astronomy. And already during the PhD, he started to pioneer transit studies of exoplanets. And there are a number of firsts. So the first transit measurement, the first characterization of a planetary atmosphere with HST, and then also first measurement of the emission spectrum with Spitzer. And I went back to the author list of the Spitzer paper, and there are a number of colleagues on this paper which are very well known here in Heidelberg, like Laurie Allen and Tom McGass. Tom just spent a sabbatical here. So in a way, we have good connections via third persons. Then David is also the PI of the Mirth Project, and I think he will touch on that because he's extending this project to the southern sky now. He's a member of the Kepler science team and also the test team. And for his achievements, he earned a number of prizes and awards, and I will not go through the list, but I will only mention one, which is a very recent one, the Sackler Award, given by the Tel Aviv University, which is really a very nice prize for his achievements. Today, he will actually talk about a fast track to find even inhabited exoplanet. I think there is a very fast track. There is at least one here, but I guess we're searching for another one. So David, welcome again, and we are looking forward to a nice talk. I think you need this.
Yeah. Thank you, and thanks for the opportunity to speak. What I want to do today is talk about a really exciting field in astrophysics. I'm going to show you today a lot of results, some of which were announced only 6 days ago, and some of which were announced only 12 hours ago. So it's a very timely talk, I hope you'll find. I know that not all of you work on exoplanets yet, so I wanted to give a brief introduction for those of you that are not yet persuaded. And so really my goals for today are four. So I want to first describe the methods by which we find and characterize exoplanets to make sure we're all on the same page. I want to motivate why, as physicists, you might find this subject intriguing. I think there are a number of very interesting hooks for everyone in this audience. I want to describe the current state of knowledge, particularly of low-mass exoplanets, which is really where the field has moved to in the last few years. And I want to present an opportunity for rapid progress, which is really what is hinted at in the title. Okay, so those are my modest goals for today. I want to begin by thanking and acknowledging my research group. I'm showing you here the names of recent alumni and where you can now find them. I want to highlight some names. These are the individuals whose work I'm going to highlight today. I can't cover everybody's, but I think this work comes together into a nice, tight story. And so I'll be showing you the work of Sarah Ballard, who is now a Sagan Fellow at the University of Washington, as well as the work of Zach Berta, Jonathan Irwin, Francois Fressin, and Courtney Dressing. Okay, so among the ways that we have to find exoplanets, two have risen to be the most productive to date. The first is the Doppler method, or the radial velocity method. And so here the basic idea is we don't initially see the light from the planet directly. We see the light only of the star. And we can measure very precisely the radial velocity along the line of sight to the star by looking at the wavelengths of the absorption features, the lines that appear, the Fraunhofer lines that appear in the stellar spectrum. For some stars, we see that the Doppler shift undergoes an oscillation. And so the star is being accelerated, and we can conclude that there must be a dark companion, a planet to that star, and we can deduce the mass of that planet. Then there's another method that we have to find and characterize exoplanets, and that's the transit method. And so here, if our line of sight is fortuitously aligned to the orbital plane of the planet, then when the planet passes in front of the star, you'll see a little eclipse. And so the planet will block some of the light from the star, and you can measure the relative size of the planet to the star. When you have the mass of something and you have the radius of something, then as good astronomers, we can plot those things against each other. And I want to show you what that plot looked like 4 years ago when I last visited here. And then I'm going to leave all of that behind. Okay, but I want to show you how quickly the field has moved ahead in 4 years. So 4 years ago, I didn't show this exact plot, but this is the message that I sought to convey. Here we're showing the radii of known exoplanets, and here we're showing the masses of known exoplanets. And all of the planets we knew about were large gas giant planets close to their stars. Those were already intriguing to us as physicists because we could compare the radius of an observed planet to its mass and to theoretical predictions of what the radius should be given its mass. So if you think you understand the equation of state of hydrogen and helium, then you should be able to tell me if I give you a ball of hydrogen and helium and it's got a certain mass, it should have a certain radius. And what we found even 4 years ago was that we had a basic problem in the physics of these planets. Most of the planetary radii were much larger than the prediction of the model, which is shown as the blue line. Okay, so you can see the model does a good job at Jupiter and Saturn. It does a rotten job, and this problem persists to this day. We don't really understand the physical structure of most exoplanets for which we have good measurements of their masses and radii. At lower masses, we're going to use the equation of state to make a guess about the composition. So the hope 4 years ago was that if we were to push down into this regime and find planets that really were similar to the Earth in mass and radius, then by very precisely measuring the mass and the radius, we could actually deduce where the planets were, for example, rock and iron, as we know the Earth to be, or had large compositions of water, which would reduce the overall density, or even hydrogen-helium envelopes. We wanted to see whether the planets of the solar system were typical or not. Learning about the composition would tell us about the formation of these planets. Learning about whether they are enriched in iron, whether there's no iron, whether they have large envelopes of hydrogen and helium, is probably one of the very best clues, as it is in the solar system, for reconstructing the history of how these planets came to be, and therefore the physics of planet formation. And finally, what we've learned is we're now finding planets in systems, and there's a fascinating a set of orbital resonances and architectures, and reconstructing the formation of these planetary systems by understanding and studying the current multi-planet systems is also proven to be very fruitful. The other reason I'm really interested in transiting planets, and in fact there's a workshop going on right now that I'm participating in, is to talk about this topic, which is they allow the opportunity to study the atmospheres. So you might imagine the way to get at the atmosphere of an exoplanet is to take a very high spatial resolution image, and you've got your star over here, and you spatially separate the light from the planet and the light from the star. Having done that, you then perform spectroscopy upon the planetary emission, and you search for molecules and begin to understand the physics of the atmosphere. We can't do that, and we are nowhere near being able to do that for planets that are truly the peers in age of the solar system. So when planets are really young and hot, and widely separated from their stars, and strange in all respects compared to the solar system, then yes, we can take an image and we can study the spectrum. And that is tremendously interesting. But that's only been able to be done in a few rare and very young cases. For the vast majority of planets that we now know about that are similar in age to the solar system, the planets are cold and they don't emit much light. And so we had to come up with a trick. And the trick that we came up with, which we think has been very fruitful, is to use the light now as a probe instead of being an impediment to studying the planetary atmosphere, to use it as a probe to get at the planetary atmosphere. So what we do is we wait for the planet to pass in front of the star, we observe the starlight passing through the atmosphere, and imprinted upon that starlight will appear the chemical absorption features of whatever atoms or molecules are present in the atmosphere of the planet. Using these techniques, and a similar technique when the planet ducks out of view behind the star, has allowed for the detection of a few atoms and molecules, the inference of stratospheres, so the fact that as you go up in the planetary atmosphere, the temperature increases instead of decreases. Of course, very different than stars, but a commonplace in the solar system. Most planets have stratospheres. Clouds are now being inferred, and even winds. We're even seeing the dynamics as these strongly irradiated planets try to deal with the enormous amount of stellar radiation and advect that around to the night side. So I think that this opportunity presents further motivation for us to really go out and carry out these studies. Pardon me. Sorry. No, it's all right. I'm sincere. So you know, if you're not engaged in exoplanet studies, or maybe not even an astronomer, I just want to comment that what I've seen is the quest to go and characterize these planetary atmospheres has given rise to some really novel optical experiments. And in talking to my colleagues in physics, I think many of them have just been intrigued by the novelty, the imagination, and the very interesting optical design that's gone in increasingly to these experiments that are being proposed. Finally, of course, there's the question of life in the universe. And while that is not a question that's going to be restricted to astrophysicists, we're very fortunate that it falls to us to answer it because we have the technical ability. We have the large telescopes, we understand the optics, we are the ones who are able to gather and analyze spectra. And so even making modest progress on this great question, arguably the greatest question in science, would be fascinating. And so I think that's also a tremendous motivation for us. Okay, so I want to show you a couple observatories that have been very fruitful at getting at these exoplanet atmospheres. For example, there's the Magellan Observatory. These are 2 telescopes in Chile. Harvard, my home institution, is a partner in these. I could have equally shown the very large telescopes, the European 8-meter class telescopes that have allowed a lot of penetrating studies of these atmospheres. Similarly, we've done great work from space. The Spitzer Space Telescope, despite a very modest aperture, right? It's smaller than 1 meter in size. It's in a heck of a location, okay? It's in a heliocentric orbit, and so it's incredibly stable in time. And so what that means is you can use Spitzer to wait for the planet to pass out of view behind the star. And you might think, well, how does that help you study the atmosphere of the planet? Well, the idea is you can take a spectrum then of the star in isolation. You can wait for the planet to come back into view. You can repeat the observation where now you have a spectrum of the star and the planet, and you can subtract those. And when you subtract them, the star goes away, and the light that's left over is the light of the planet. Spitzer is essential for doing such studies because its orbit means that it's very stable in time. So when we see changes in time, we can reliably associate those to be due to the astrophysics and not due to variations in the instrument. Okay? Well, now let's think. Are we building other big telescopes in Chile? Yeah. Are we putting other large infrared telescopes in space? Yes, yes we are. Okay, good. So let's show a picture of them. Right. So at Harvard, we're part of a consortium to build the giant Magellan Observatory for the modest cost of $1 billion. Many of you are engaged in the European Extremely Large Telescope, a much more ambitious and costly endeavor. Similarly, in space, we are invested in launching the most powerful observatory ever created, the James Webb Space Telescope, which we believe will cost $8 billion. Is it possible that these observatories will do for Earth-like planets what Spitzer and the VLT did for gas giants? Yes, it's possible. They'll have the additional photon gathering ability, they'll have enormous stability, they'll be able to do these penetrating studies of exoplanet atmospheres. What's the problem? The problem was we do not know where to point these observatories. We do not yet have the examples of the very closest transiting small rocky planets. We know, based on results from Kepler, that they must be out there. We haven't yet identified them. So for example, if we had the ELT and we had the James Webb today, we would actually be wasting our time. We would not know which stars to study in order to get at these rocky exoplanet atmospheres. What's the challenge? Well, here's the challenge, okay, in a nutshell. Do you see it? Right. Okay, so there's the Earth in front of the sun. Okay, if you're sitting at the back of the room, maybe you think I should be pointing here or here. These are spots, which of course are often much larger than the Earth. The challenge is to detect such planets orbiting sun-like stars. They block so little of their starlight that we have to get exquisite precision. Okay? So they block less than 1 part in 10,000 of the light from the star. And so if you want to go and detect exoplanets like the Earth in front of sun-like stars by their transits, you have to build a machine that's capable of monitoring large numbers of stars, because only a tiny fraction might have a planet and only a tiny fraction of those might transit, so that you can actually see these little signals, which happen only once a year. The machine that did that and that broke open this big piggy bank of rocky planets is the Kepler mission. So the Kepler mission was a big part of my life for about 5 years. It was an enormous part of another man's life, Bill Barucki, who's the PI, for 25 years, as he sought to convince colleagues that this would revolutionize exoplanets, and he ultimately succeeded. Kepler is a 1 meter Schmidt telescope. It launched in March of 2009. It began gathering science data in May, and it gathered science data successfully for about 4 years, and as many of you know, due to the failure of a second reaction wheel, it no longer is gathering high precision photometry. But Kepler, in those 4 years, simply revolutionized our understanding of small rocky planets orbiting other stars, and I want to just highlight a few results. First of all, I want to emphasize that the Kepler photometry is exquisite. So here I'm showing unpublished work led by my student, former student, Sarah Ballard. And what Sarah did was to pick a particularly interesting exoplanet. It's not yet dubbed a planet, so it goes by the name of Kepler Object of Interest, KOI, 69 in this case. And I want to show you how precise the Kepler photometry is. So here is a very well-measured exoplanet transit. Please take a note of the y-axis. Okay, so this is a change in brightness of 1 part in 10,000. Okay, so you can see the enormous signal to noise. Here, the overall change is maybe 2.5 parts in 10,000. The unsung, I would say, story of Kepler is the Astro Seismology. Okay, you hear so much about the exoplanet results, you forget that actually this is probably the greatest Astro Seismology mission instrument ever created. Why Sarah was so interested in this one exoplanet was because she was able also to detect the beautiful spectrum of the Astro Seismic signal. And so if you plot the power spectral density of the 4 years of Kepler data, which were gathered at this 1 minute cadence for essentially 4 years, then of course you detect all these exquisite oscillation modes. And these are sound waves propagating through the star. And because they trace different chords through the star, they probe different densities. They probe different depths into the star. That tells us about the evolutionary state of the star, as well as gives us a very exquisite measurement of, first of all, the density, and then, as a result, the mass and the radius. So typically, when all you have is a light curve, even a very precise one, your actual knowledge of the radius of the planet is poor. Because although you measure the relative size to the star very well, actually telling me the radius of the planet in kilometers is very difficult, because you have a large uncertainty in the radius of the star, maybe 10%. Once you have the astroseismic detection, then you know the radius of the star extremely well, and so you can really lock down the parameters. And so in this case, what Sarah was able to determine was that what we have here is a 1.48 Earth radius planet. She's measured that number to a precision of just better than 100 kilometers. So think about real kilometers. Here we're doing extremely precise measurements of bodies not much larger than the Earth. Excitingly, she was also able to determine the age of the system. The age is very important. If we think about the Earth, how did the Earth look when it was 1 billion years old in terms of the atmosphere? What might it look like when it's 10 billion years old and life has been doing its thing for several more billion years? So planets evolve over their lifetimes. If you go out and get a spectrum of a sun-like star and you do your best to characterize it, you have a very hard time distinguishing between a 1 giga-year-old star and a 4 giga-year-old star and a 7 giga-year-old star. And if the stars are just a little bit lower in mass, you really have no constraint at all other than saying it isn't terribly young. So in terms of really understanding these planets, the Astro Seismology, which now is telling you the age to better than a giga-year, is an enormous leap forward. Of course, Kepler is not only a machine for finding individual systems, it's primarily a machine for doing statistics. And so here I'm showing the work of François Fressin, who is a postdoctoral fellow working with me. And what François did was, I believe to date, this is the current best understanding of the exoplanet population as derived from Kepler. Okay? So Kepler is very good at measuring, of course, the radii of planets. And here he's showing the number of planets per star. He only goes out at this paper to a period of 85 days. And that's because at the time that he analyzed the data, we only had several times that amount of baseline. And so we only reliably detected transits for planets that were in orbital periods of less than 85 days. And what Francois found was that Earth-like planets, small planets, vastly outnumber gas giants, okay? So, you know, for a decade, we've been studying gas giants orbiting sun-like stars. We now know for sure that at least for relatively short periods, these are but a humble minority compared to this enormous population. He also established that the rate of planets is roughly constant, and this is fascinating constraint on models of planet formation between Earth-sized and Neptune-sized, roughly 4 times the size of the Earth, including a kind of planet we don't have in our own solar system. There are many, many planets out there that are 2 or 3 times the radius of the Earth. Those are really unconstrained based on the solar system. We don't really know if those are large balls of rock or if those are mini Neptunes. Importantly, he was able to constrain that at least 16% of sun-like stars have an Earth-sized planet. That doesn't mean an Earth-like planet. Most of those are much too hot to have life, but it was a first firm constraint on the size, on the population of very small planets. So here's a first result that really is very recent. This was just announced yesterday at the Kepler Science Conference, which is going on at the NASA Ames Research Center. There was a study done by Eric Pettigura, Andrew Howard, and Jeff Marcy, and what they were trying to do was take a first swing at the big question from Kepler. Kepler's top goal is to tell us what is the rate of occurrence of Earth-like planets orbiting sun-like stars. That means planets that are the same size as the Earth, planets that are the same temperature. How common are such planets in the galaxy? And so they picked the 42,000 bestest, sunniest stars that they could. They did their own search, and in doing their own search were able to characterize the incompleteness. They were able to figure out for each star how small a planet could they have seen. And then they highlighted all of these are planets that were detected by their own search. They verified that they had also been detected by the Kepler pipeline in most cases. And then they drew a box around things that were roughly Earth-like. And they said that roughly 20%, the number is roughly 20% of sun-like stars have an Earth-like planet. Now, before you lock that number into your lectures, let's stop for a moment and realize that it's an intriguing study because they actually didn't detect a single Earth-like planet. Okay? So they're telling you the rate of occurrence of Earth-like planets, but they didn't find a single Earth-like one. They're very straightforward about this in their paper. I don't mean to imply that they're not telling the whole story. And they have to extrapolate. And they're nervous about this, but they realize that this may be it. This may be all the data we're going to get from Kepler. Many of us hold out hope that with a further investment, we can refine the data analysis from Kepler, and the precision will get better, and more planets will pop out of the pipeline. But if that's not true, then we might as well try to estimate this crucial number. So the point is, these are the planets that were deemed to be roughly Earth-like, but notice that they range between 1 and 2 Earth radii. A 2 Earth radius ball is almost certainly not Earth-like. It would be very difficult to have that be pure rock. It very likely has a significant envelope of hydrogen and helium, and so it wouldn't be habitable, at least as we know it on Earth. Similarly, they broaden the definition of irradiated flux. So here they're showing the stellar light intensity scaled to Earth units. So a planet that was receiving the same amount of energy from its star as the Earth receives from the sun and was 1 Earth radius would fall right here. There are no planets that fall right there. There are a few planets that are a little bit bigger, and there are none that receive less energy. The Earth, many think, is close to the inner edge of the habitable zone, and so planets that receive 4 times as much energy, which delineates the green box here, are also probably not habitable. Nonetheless, I think this is a good first crack at this question. If they stop and consider what fraction of stars have planets, they notice that it's roughly constant in logarithmic interval. And so they can then extrapolate and say, well, let's really restrict to planets that are only 40% larger than the Earth, those probably are rocky, and only planets that receive as much energy as the Earth or less, and then the number drops to 5%. So probably 5% of sun-like stars have an Earth-like planet. Great. we now have a really exciting set of planets. Let's go and actually characterize them. So looking ahead at what we might do for Kepler, Kepler allows us to detect these Earth-like, or at least Earth-sized planets by transits. The next thing we certainly want to do is go and measure their masses. And as I'll show, I think we have a way to do that. So that'll give us a bulk density, and that'll inform models of the formation. If you really want to go after understanding the composition of the atmospheres, I think you're going to be out of luck for Kepler. Why? Because the stars are far away. In order to do statistics, Kepler had to cram enough stars onto its field of view, so the typical star is quite distant from us, and it's a large sun-like star, and so the atmosphere simply presents too humble a signal compared to that large, distant star, that we're going to have a very hard time. We don't gather enough photons during an exoplanet transit to be able to go and characterize the atmosphere of the Kepler planets. So while Kepler tells us a lot about the statistics, it offers very few opportunities for direct characterization. What we need are a population of such planets informed by Kepler, but much, much closer to the Earth. Recently, NASA selected the next Explorer-class mission to launch. And I was a small part of that team, and this is called the TESS mission. We're very excited about TESS. TESS is one of these quick turnaround, relatively low-cost missions. The basic idea is it consists of 4 camera lenses. And these 4 camera lenses will scan the sky, spending 1 year on the northern hemisphere, 1 year on the southern hemisphere, and unveil to us the population of all the nearby stars with transiting planets. It won't do a lot for statistics. It's very hard to beat Kepler for statistics. But what TESS will do is find many, many, many of the closest ones, and so we can pick subsets of rocky planets, subsets of Neptunes, subsets of gas giants, break them up by spectral type, and really go and characterize them and understand the relationship between the planet and the star. If we didn't fly TESS, and we asked, how many stars do we have that are bright enough to actually allow us to go and characterize their atmospheres, then this would be essentially the list of stars that we have to study. These are all the stars, after 15 years of hard work, these are all the stars that are brighter than 10th magnitude that have a transiting planet and would allow us to do these atmospheric studies, okay? And as you can see, almost entirely they consist of these very hot Jupiters. So we do know about nearby bright stars with hot Jupiters. There's a couple examples of small Earth-like planets orbiting relatively nearby stars, but it's really hard to get excited about sending forward characterization experiments if this was the only population that you had. Here's what we currently predict the yield to be after the TESS mission. So the point of TESS is clear. It will provide the international community with a reservoir of thousands of Earth, super-Earth, Neptune-sized planets to go and characterize. Unlike Kepler, the TESS data will become public immediately. So the people on the science team are working very hard. They don't get any proprietary period. Okay, so the reason I'm telling you about this is if you're an undergraduate and you're thinking, what kinds of things might I do in graduate school? You know, TESS is going to fly in 2017. So this will impact that timescale. If you're a graduate student and you're looking ahead to postdoc or to research years 5 or 10 years out, I really think that Kepler and then TESS will really dominate the landscape during that time. I said we had a way to go and get the masses. I'm currently on sabbatical at the Geneva Observatory. What brought me to Geneva was for the past 7 years, we've been working with our colleagues to build a copy of their ultra-precise radial velocity machine. They had one in the southern hemisphere called the HARP spectrograph. We thought, good idea, wrong hemisphere. Why? Kepler only looked at stars in the northern hemisphere, so we couldn't do the mass measurements. So we started to find all these Earth-sized planets, but we couldn't actually know what were they made of. And so we made a copy of HARPS. We are collaborating with the Italian community. It's located at the Italian National Telescope, as well as with several universities in the United Kingdom. And we brought this online last year, and so the reason I'm at the Geneva Observatory is now the data is really starting to flow, and we're starting to see our first exciting results. And the goal, one of the main goals of HARPS North, is to go and try to measure the masses of a large number of Earth-sized and super-Earth-sized planets that were discovered by Kepler. What was so impressive for me with HARPS North was they turned it on, and literally within a few weeks, they got to the point where you would take a spectrum, it would tell you the rate of velocity, and the precision was good to 1 meter a second. That the scatter, the ability to measure the rate of velocity of the star out of the box, because they had the benefit of such a similar instant in the southern hemisphere, was 1 meter a second. One activity that we're very involved with at Harvard and the Smithsonian Astrophysical Observatory is to look forward to really push the precision. So the Earth induces an acceleration on the sun of 9 centimeters per second over the course of the year. And so 1 meter a second is not good enough if you really want to push down to Earth's. So we're trying to think, how might you push the precision of such a nice spectrograph down from 1 meter a second? I remember when I was in graduate school, the precision was 10 meters a second. And everybody said, oh, they're never going to do better. And then it dropped to 3 meters a second, then it dropped to 1 meter a second. Now we're working at 1 meter a second, and we have these naysayers who say, oh, you'll never, oh, that's the best you can do. Can't do any better. But you watch, we're going to go down to 50 centimeters and 10 centimeters, and then we're going to be using this method to measure the masses. There's a very tricky astrophysical problem, which is the jitter of the star. There's also the challenge of calibrating your spectrograph. And so what we're doing is we are collaborating with laser physicists who have built what we have called the Astro Comb. This is really the work of Dave Phillips and Ron Walsworth and Andy St. George, and so I'm showing their work here. It consists of 3 elements. There's a laser frequency comb, which creates a very dense set of lines for which we know the wavelength exquisitely. It's too dense, and it's at the wrong initial set of wavelengths, and so we use a photonic crystal fiber, or you need some other kind of nonlinear element to shift, to boost you into the wavelength regime that you want, where most of the stellar lines are, so that you can calibrate the appropriate wavelengths. And then you need a filter cavity to snip out all but 1/20th of the lines, because otherwise it's vastly too many lines for our spectrographic resolution. We're on Sky at HARPS. We've been on Sky at HARPS since January. I want to just show what it looks like. You can see there are 2 fibers. This fiber here shows you the sun as observed by reflecting off the asteroid Vesta. And these lines are the laser frequency comb. So does that look like a good wavelength calibrator to you? Oh, you're so unemotional. Yes, I think that's a good wavelength calibrator. Okay, so the point is, if you've done this kind of work before and you've worked with thorium-argon, you know, in any one order, you might have these big, blotchy thorium-argon lines, you might have 10, you might have 20. You cannot, I mean, there is a fundamental physics property, which is atomic clocks at the heart of this. This surely is the way to calibrate spectrographs to centimeters a second. And this is just a quick slide showing we're calibrating the spectrograph to 10 centimeters a second. That has not solved the problem, because we have to get at the astrophysical jitter as well, but we really think we're there, or going to be there shortly. And there's all sorts of interesting things that pop out of that as well. Okay, so what's the promise of HARPS North? The promise of HARPS North is to tell us about the relationship between mass and radius, and therefore composition, for Earth-sized planets. So this was the lay of the land as of 7 days ago. Okay, so when I started the talk, I showed you how things looked 4 years ago. This is now a tiny corner in the bottom lower left-hand part of that plot. Okay, so before I was showing you things up to 20 Earth radii and 1,000 Earth masses. Now I'm going as high as 2 Earth radii. Okay? This is where the field is, and we're going to go up to only 10 Earth masses. So keep in mind, Jupiter is 11 Earth radii and 300 Earth masses. Okay, so the promise of HARPS was to really fill in here. Why? Because if we start to populate, then we could tell, do we have planets that are primarily water? Do we have planets that are pure silicate or iron? Intriguingly, do we have planets that lie below this line? That's the maximum mantle stripping line. So the idea is, if you make a planet out of the stuff that we think you have in your protoplanetary disk, you have to have a mixture of iron and silicates. The iron, however, will sink to the core of the planet, so there's a trick to making an iron-rich, a very dense planet, which is a series of impacts could knock off the mantle, as we think happened a little bit for the Earth, made the moon, right? So you could imagine removing the mantle, but there's a limit to that process. And we think that limit is described by this black line. Intriguingly, the planets seem to know about that line. So do they know about the line going forward? Okay, so 6 days ago, we announced the first planet firmly in that regime. This is Kepler 78. Kepler 78 is exciting to us because it truly is only a smidge bigger than the Earth. It's 1.1 Earth radii, and lo and behold, the mass is exactly what you would expect to lie between pure silicate and this maximum mantle stripping model. This was accomplished with HARPS North, but independently, and this was done through a very nice collaboration with colleagues in Hawaii and in California. It was also independently measured with the Keck high-res instrument. Okay, so, and also I promise there are more points to come in this regime. And I think a year from now, you'll have 10 points in that yellow box, okay? So that's really exciting times. We really are getting there. Okay, great. So now, back to, so that was about compositions, masses, and radii. How are we gonna get at the atmosphere of such a small planet if it transits a sun-like star? And I'd like to make the case that we can't, that if you want to study the atmosphere of an Earth-like planet orbiting us, maybe you think there's something about a sun-like star that uniquely permits life. Or maybe you don't care about life, but you just want to find analogs of the Earth and say, do they have the same atmospheric physics? Do they have the same composition? What makes Venus Venus, and why was the Earth different? Was it just their slight difference in proximity to the sun? What if you changed the star a little bit? There's no way to get at the atmosphere if they transit sun-like stars using the techniques I outlined. There are very ambitious plans to image such planets, which would allow you to study the atmosphere. Those are, I believe, at least 25 years away. So I'm not that old, but I'm already nervous about committing to such projects because it's so expensive and we don't have the money. I think they're worth thinking about, and there's good people thinking about it, but what I'm going to outline, and that's what I want to do for the last part of my talk, is that we don't have to give up hope. There is a way to study the atmospheres of Earth-like planets, potentially even habitable planets, but we have to be tricky. The trick is to realize that I was lied to in high school. Maybe you were told the same lie. I was told, you must have been told this before you became an astronomer, the sun is an average star, right? Okay, so forever now, let us dismiss with this idea. The sun is a freakish star. It is much more massive and much more luminous than almost all stars in the galaxy. Small M-dwarf stars that are about 1/5 to 1/10 the radius, 1/5 to 1/10 the mass, outnumber us at least 10 to 1. Okay, so we are not that relevant from a perspective of individual potential sites for Earth-like planets. So here I'm just reminding you, showing you to scale what a sun-like star would look like, what an M6 star would look like, and then what the Earth would look like. And this is a nice slide provided by Jacob Bean. If you are beginning to believe some of the ideas I've thrown out there about transits and radial velocities and opportunities to characterize through atmospheric studies, M-dwarfs are wonderful. Everything goes in your favor in terms of detectability. Okay, so let's consider a 2 Earth radius planet in the habitable zone of an M-dwarf. Okay, so if you want to go and detect the planet, you have to go to space if that same planet were to orbit a sun-like star. It blocks too little of the light. You need a mission like Kepler. But if that same planet is in the habitable zone of an M-dwarf, it blocks almost 1% of the light. We've been doing 1% photometry and detecting planets for 15 years now. Okay, so that's duck soup. Then, if you want to go and measure the mass, the wobble is greatly increased as well for 2 reasons, right? The wobble is much bigger. One is that you're kicking around a much lower mass star, and also the habitable zone is tucked in close, so you're much closer to the star. So you induce a much larger wobble, and so the wobble for a habitable super-Earth is already significantly above the current limiting precision, let alone the Astro Comb results that I showed. The transit probability is bigger because the planet is closer to the star. And of course, the orbital period is much less, right? So instead of taking a year, because in the habitable zone of a sun-like star, you have to be a year orbital period, the orbital period now might be 1 or 2 weeks. So, so it seems to me this, you know, I'm a opportunistic when it comes to exoplanet studies. I think that's where so much progress has come from, is people seeing opportunities that were there in front of us. This, to me, screams opportunity. So seeing that opportunity, I set out with Jonathan Irwin and Philip Nutzman and Zach Berta a few years ago to construct the Mirth Project. So we're looking for Earth-like planets around M-dwarfs, so we call it Mirth. And the idea of Mirth is there are roughly 2,000 M-dwarfs that are smaller than 1/3 of a solar radius in the northern hemisphere and within 30 parsecs, okay? So let's go and actually search all of them for small planets that might even be in the habitable zone. And so we did a large design study that was really the work of Philip here. You're seeing his back. And he decided what you needed was 8 40-centimeter telescopes, and then you could do that survey with off-the-shelf CCD detectors. Okay, now Mirth is different than most transit surveys. Most transit surveys simply stare at one patch of the sky, and they stare continuously. They see all sorts of stars that get periodically fainter, and then they sort through that. Okay, a lot of those are eclipsing binaries, some of them are statistical false positives. We don't have any of those problems. In each of our fields, there's only one star we care about. There's one M-dwarf. Since we're surveying the 2,000 brightest ones, they're all over the sky, so we can't fit them all into one field. And so we need 8 telescopes, and these 8 telescopes can search around and around and around. And I want to briefly show you the movie, to show you what that would look like. I want to say we've expanded. We're in the northern hemisphere in Arizona. We've now expanded to the southern hemisphere, to Cerro Tololo. My understanding is this building is going to be finished construction on Friday. So I'm very excited about that. I think they're going to put the weather's not that good. They have to put a roof on it, don't worry. Okay. So this is a time-lapse movie of the Mirth Project. What you're seeing here are 8 telescopes, okay? So there's 1, 2, 3, 4, 5, 6, 7, 8. 8 telescopes, and the roof is closed, the roof now opened. Because of the German equatorial mounts, we have to do a crazy calibration dance. And then what the telescopes do is they have a list. So each telescope might have a list of 10 or 15 nearby M-dwarf stars. And it looks at star number 1, it looks at star number 2, it looks at star number 3, and then it gets back to star number 1 on a timescale of 20 minutes or less. Why? Because the transits last about an hour, and we don't want to miss them. The trick to Mirth is it's a real-time trigger. Okay, so the telescopes are surveying these stars, but immediately after taking the data, they ask, is the star fainter than it should be? Namely, is it fainter than it was 20 minutes ago? And folding in all the information I've gathered over the observing season. If they determine that a star is fainter, then that telescope stops what it's doing, goes back, and then repeats continual monitoring of the star in question to observe the egress as the planet leaves the stellar disk. And it can even ask its friends in the network to go and join in. Shortly after we started Mirth, we discovered GJ1214. So GJ1214 got us very excited because you can see this was the state of knowledge at the time of the discovery. Again, these were the population of gas giants, and all of a sudden we had a planet down here. Only one other planet was known down here, that was Corot 7, but it was impossible to study the atmosphere of Corot 7 because it is far away and it orbits a massive sun-like star. GJ1214 was different. GJ1214 immediately posed some interesting questions. Its density was intermediate between the Earth and Neptune. Its size and its mass were intermediate. So we didn't have anything in the solar system like GJ1214, and so we asked ourselves, what could it be? If all we had was the mean density, then we would forever have a fundamental degeneracy. GJ1214b could be a water world. It could be essentially a big ball of water. The density would work out just about right. It would have a small core. Or it could be a mini Neptune. It could have a significant overlying envelope of hydrogen and helium, but a denser central core of silicate and some ice. And those are fundamentally different. Did it form like Neptune? And by consequence, are the thousands of planets that Kepler has discovered that are 2.5 Earth radii also like Neptune's? Or are those planets really water worlds, or potentially even rocky worlds? How could we resolve this question? If all we had was the mass and the radius, and that's going to be the case for the Kepler planets, this would be the end of the story. But something was different about GJ 1214. Here I am showing an opportunity plot, okay? So the plot is, here I'm going to show you two things you really care about for the planet. The first is the planet radius, okay? So what is the size of the planet? So obviously really interesting planets are maybe down here, the larger gas giants are out here. And here I'm showing the transit depth, okay? And the transit depth is a measure of how easy is it to study a planet. So you can see that if we plot all of the known Kepler planets and all other planets discovered ever by all other surveys, they know how to precisely avoid the easy and interesting part of the diagram, okay? Interesting because they're small radius, easy because they're large transit depth. This function goes out of its way to avoid that part of the diagram, but GJ 1214 is different. That was the whole motivation. If we could find a few planets like this, we could suddenly study their atmospheres, even though they themselves are only slightly more massive than the Earth. I'm not going to go into the details, but we succeeded in doing that. We instantly went and, this is the common story in exoplanets. You discover something with a small ground-based telescope. You then go and get large amounts of time on the most powerful observatories ever created. We convinced the Hubble Space Telescope to give us some time. And we said, if this was a mini Neptune, if the atmosphere was large, if there was a large envelope of hydrogen and helium, then we will see this red curve. And we went and got the data with the WIFC 3 camera. And the data are shown in black. Are those data a good fit to the model? No, thank you. Those data are a terrible fit to the model. We can rule out that model. And then we said, well, if instead we have a planet that was a water world, so it wouldn't have this big puffy atmosphere, because the mean molecular weight of the atmosphere is higher, the scale height is smaller, the atmosphere is compressed, there's no variation in the spectrum, in the transit depth as a function of wavelength, and we found that that was a very good fit. There is another interesting and equally viable hypothesis, which is clouds. So we ruled out the idea of essentially a solar composition envelope. But it is possible that we have a water world. It is possible that we have something with a significant envelope, but there are some kinds of clouds, not clouds that make much physical sense given what we know about the planet, but possible nonetheless. And all I want to say here is stay tuned, because colleagues of mine at the University of Chicago went and did a GJ 1214 deep field. So to convey to you, just based on the numbers, how exciting these planets are. The single planet was allocated 5 continuous days of Hubble Space Telescope time, 5 days to go and study its atmosphere. And they definitively decided between those two models. I'm not going to tell you which one. Okay, and then just briefly to make the point, this is just a light curve from that data set that we gathered with Hubble. If this same planet, if you had this planet transiting a sun-like star, it would have been this deep. It would have been completely unobservable. So the whole opportunity here is created by the fact that we have a planet orbiting an M-dwarf. I wanted to say that the topic of water worlds is tremendously exciting. And Lisa Kaltenegger here in Heidelberg has really led thinking about a wide variety of what these atmospheres might look like, what the planets might be like. And I wanted to show one result because we were on the topic of water worlds. These are the currently known water worlds that are in the habitable zones of their stars. And what Lisa recently calculated, working with Dimitar Sasolov and Sarah Rugheimer, was to consider different kinds of water worlds. So these are planets that are not predominantly water, but they have a complete water surface. There is no silicate rock. There is no continent poking up. And if you know about the carbon cycle and you know about planetary physics, that completely changes the interaction between the stuff the planet is made of, the ocean, and the atmosphere. Okay, it locks away perhaps some of the relationship, the communication between things like CO2 and carbon in the mantle and in the atmosphere, the way that it would be expressed for us observers. And so, for example, here she's reminding us this is what the Earth looks like in transmission, including molecular biosignatures, ozone and its derivative, ozone and then also molecular oxygen. This is the sort of signal we could go and look for if we want to actually go and look for biosignatures through this transit method. This shows you the relative strength of those signals. Here she's showing two potential realizations of such water worlds, okay? One is a hot Earth, okay? And one is a situation in which you have a planet that's much farther out in the habitable zone, but because of a large envelope of carbon dioxide, there's a significant greenhouse effect. And although the average temperature of the planet would be cold, there still would be liquid water and potential habitability, easily distinguished by the differences in these spectra. These sorts of models are what will guide our studies with the ELTs and with the James Webb Space Telescope. And then finally, what I wanted to end with was the big question that preoccupies me for the immediate future, which is, how come Mirth hasn't found more planets? I think we're really onto something, okay? GJ1214 is arguably the most highly studied planet known, other than the first discovered transiting planet, 209458, despite the fact it was only discovered a few years ago. It's been intensively studied because of the interest in this world. Why can't Mirth, or why hasn't Mirth found more of them? And so I want to here briefly show this. We did an intensive, we simulated the results from our Mirth data set for the first 3.5 years. This shows our sensitivity. So dark means we're sensitive, white means we're not sensitive, would not have found such kinds of planets. Here I'm showing the planet size from 1 to 4 Earth radii, and here I'm showing the equilibrium temperature. So planets that are big and close to their star are easy to find. This has nothing to do with Mirth. This is the most recent analysis from the Kepler data showing the actual population of planets that we now know to orbit M-dwarfs. Oh, so foolish. Okay. So Courtney Dressing analyzed all the M-dwarfs from Kepler, and here's where the actual planets are. Dark means there's lots of planets, white means there's no such planets. Is the current Mirth strategy well matched to find the population of planets that we now know is out there? No. No, it's not. In fact, if you multiply those two, then you predict the yield of your experiment. Look where 1214 is. Okay, there's no shenanigans here. That's an honest calculation of sensitivity. This is a result of an entirely different experiment. So it's not surprising that we found a 2.5 Earth radius planet, but what this tells us is exactly how we have to change our experiment. We don't need to look at as many large stars, but we do need to push down into this parameter space, and all of a sudden there should be lots of 1.5 Earth radius planets. And so to end, the message I want to please take home the following message. If we survey nearby small stars for transits, we could identify planets that are Earth-sized and in the habitable zone. We know that they're out there, and we have a way to go and get them. The atmospheres of these planets, I think, should be accessible to the James Webb Space Telescope and the extremely large ground-based telescopes that we're all so heavily invested in. And finally, that discovering and characterizing these planets will require, I think, innovative experiments, which is kind of intrinsically interesting to us. It will really push our understanding of the physics of the formation and the physical structure of these planets. And I think it really is our best opportunity for short-term progress on the big question of life beyond the solar system. Okay? Thank you.
Fascinating talk leading from discoveries to the characterization of the talk is now open for questions.
What is the spectral coverage of Mirth?
So Mirth has a simple bandpass, which goes from 700 nanometers out to 1 micron. So in the design study, we would have loved to have been observing in the infrared, but the current maturation of the detector technology pushed us towards CCDs. CCDs are essentially perfect devices now for detecting photons. And you can buy them, they're packaged, they're affordable, they're reliable, and so that cost consideration drove us towards CCDs. But you could imagine doing a survey like Mirth at longer wavelengths. The challenge that this presents to Mirth is there's lots of water in our bandpass, and so there's a whole story in here about the secret sauce to getting, how do you monitor the brightness of M dwarfs by comparing them to sun-like stars and still do that at maybe several parts in 10,000? And the trick there was figuring out how to correct for the changing water vapor among our, above our somewhat wet site in Arizona. So, but we solved it. Right, so the joy of Mirth is that because we have a catalog of M dwarfs, for each star we have a very good estimate of its radius. And so we can actually, they're unlike other transit surveys which are at fixed integration time, we tune the integration time for each M dwarf, so we achieve a uniform sensitivity, okay? That was tuned to get to 2 Earth radii by design. So when we set out to do Mirth, we didn't have the results of Kepler, and so we simply said that we're going to go for 2 Earth radius planets. We can go deeper by gathering more photons. The way we will do that is we will operate the telescopes, we will take pairs and quads of telescopes to look at the same star. That will actually give us a big boost to the photon noise, but actually beat down the scintillation noise because they're physically separated apertures. And we've run that study, and we found that we should basically, I can pull up this slide here. This is really elegant work by Zach Berta, who's now at MIT. Basically, the way we were running Mirth, here are ellipses of constant sensitivity that tell us how many planets per year we should have found. So the old way of running Mirth means that integrating over the entire parameter space gets us about 0.3 planets per year. We ran the survey for 3.5 years. We found 1 planet. Zach then figured that by looking at fewer stars but going deeper and picking the correct stars, we could actually get to 1 planet per year. And the planet will, by definition, be a smaller planet. It has to be.
Does the short period of these planets not worry you?
Well, I try not to worry too much about most things. In what sense? Yes, no, that's an excellent question. So the question, I'll just repeat it. Does the short period worry me? The short period of these planets means that they will probably be tidally locked to their stars. For a long time, this was presented as damning evidence for them as being habitable. So you can go back and find papers that said, well, they'll be tidally locked. So the atmosphere will freeze out on the night side of the planet. More recent work, and Lisa, you've been tracking this and involved in this, is that provided you have a reasonable physical model of the planet, and the planet has an ocean, or the planet has a relatively thick atmosphere, it will have no problem advecting the heat around, moving the heat around from the constantly illuminated day side to the night side. So the previous work was almost as if saying that, you know, well, the sun is set in Heidelberg now, so don't go outside because it must be 0 Kelvin. You know, of course, there's a lag, and so I think that it's no longer a large concern. But the tidal locking does present all sorts of other interesting consequences aside from habitability. The magnetic field of the planet, all sorts of interesting things. So, yeah. Right, so just to repeat the question, M stars are very active, and are there projects to go and study the stellar flux and what the consequences might be for the planet? That's another concern that's been presented for habitability, but also just for the retention of the planetary atmosphere, right? So we know that when M dwarfs are young, they are very variable, and they also have enormous ultraviolet radiation. And so that ultraviolet radiation, if deposited deep in the atmosphere, can just drive hydrodynamic blow-off. You could blow off the atmosphere of the planet. Or perhaps later in life, even if you don't threaten the atmosphere, you could irradiate life upon the planet. So there's a number of exciting things. One thing we can do with Mirth is once we figured out how to correct for changes in the precipitable water vapor, we were actually able to get rotation periods and also look for, we actually directly measure the variability of the star, the brightness of the star. We built a machine for measuring, as it turns out, we built a machine for measuring rotation periods. And so Mirth is, 90% of the publications for Mirth are not about planets, they're about the variability of M dwarfs. There's a lot of exciting work to go and try to reconstruct the ultraviolet spectra of M dwarfs at young ages. And the truth is, we don't actually know the ultraviolet spectrum of most nearby M dwarfs. And we don't really have a good facility to go and do that on a large scale. And we don't really have a lot of young examples to really know what was the very short wavelength radiation when the M dwarfs were only a few million years old. So yes, I think it would actually be hard to understand Earths and Neptunes. You're going to study the atmosphere. It's hard to understand. We know that atmosphere, in the case of Earths, is probably the consequence of a secondary atmosphere. It's probably an outgassed atmosphere. But the other mechanism which removes the atmosphere is surely impacted by the stellar flux, and we're missing that big part of the puzzle. So all I can say is it's a very exciting question.